Hello everyone, my name is Mendpara Shubham. My enrollment number 25044. Today I will be presenting about my case study project related to digital electronics, design and implementation of a 4-bit ALU. Arithmetic Logic Unit is using combinational circuit as a part of a digital design. In this presentation, we will understand what is ALU and how it works internally, how we can design simple ALU using basic logic gates. So let's move on to next slide. The Arithmetic Logic Unit, or also known as ALU, is one of the most important component of any processor. It is located at the core of the CPU and is responsible for performing all arithmetic and logical operations. Every calculation, whether simple addition or complex decision making, ultimately depends on the ALU. All the operations inside ALU are performed using binary values, meaning everything is processed in a form of ones and zeros. What makes the ALU interesting? It is inbuilt entirely using combination circuit, meaning it has no memory and produces output purely based on current inputs, like 0 for low and 1 for high. And next, an ALU is a digital circuit that performs both arithmetic and logical operations. Arithmetic operations includes addition, subtraction, while logical operation include AND or XOR on a binary integer data. It is combinational circuit, meaning that its output depends on present input and not on past values. In a 4-bit ALU, both input and output values are 4-bit binary numbers. This means it can represent number from 0 to 15 in unsigned. So arithmetic function, as I said earlier, addition, subtraction, increment, decrement, logical gate this and or XOR not, and NOR, shift functions like left shift and right shift. Now the role of ALU in the CPU. The ALU acts as a computational engine for the CPU. First, the control unit fetches instruction from memory and decodes the operation type. The ALU performs the required instruction and sends the operand to the ALU. The ALU performs the required operation, produced a result. Finally, the result is stored back in the register of memory. This process happens extremely fast, allowing modern processors to execute millions of operations per second. First fetch, then decode and route, execute and store. Then the basic operations of a ALU. A 4-bit ALU performs two main types of operations, arithmetic and logical. Arithmetic operation include addition, subtraction. Then subtraction is implemented using the two's complement, which allows us to the same hardware from both operations. Logical operations include AND, OR, and XOR. Each operation is selected using control signals, also called as select lines. As I said earlier, AND, OR, and XOR gate, addition and subtraction. Types of ALUs. There are mainly two types of ALUs, simple and complex. A simple ALU is a limited number of operations and uses a minimal hardware. It is commonly used to microcontroller and educational systems. A complex ALU supports many operations, mainly used in microcontroller educational system, as earlier said in simple ALU, and in complex ALU it supports many operations like multiplication, division, shifting. It uses advanced designs, and it is found in modern CPUs and GPUs. So in our laptop, we use complex ALUs. Now, block diagram of an ALU. The block diagram shows the structure of 4-bit ALU. It has a two input A and B, each are 4-bit. Control lines determines which operation is performed. Then the ALU can contain adders and logic gates. A multiplexer selects the final output based on control signals. It also generates flags like carry and zero, like we zero flag and carry out flag. Now inputs and outputs. The ALUs has a several of inputs and outputs. Input includes operands A, operand B, select lines carry in. Output includes the result, carry out flag, zero flag, and overflow flag. These outputs help in decision making and further processing. Now combinational circuit in ALU. A combinational circuit produced output based on only on current input. It has no memory elements like flip-flop. This makes it predictable and fast. All ALU are based on combinational circuit. As we mentioned earlier in our title block, that ALU implementation using combinational circuit. The ALU is built using basic logic gates such as AND, OR, NOT, and XOR gate. Each gate performs a simple Boolean expression. By combining these gates, we can perform complex operations. As I mentioned, AND gate, NOT gate, OR gate, and XOR gate. Takeaway is a simple 4-bit ALU demonstrates low complex computational behavior from the interconnection of a foundation concept of digital system design. The AND gate Now the AND gate in a ALU. The AND gate output is 1 when the both inputs are 1. That we can see in truth table is when A is 0, B is 0, we get 0. When 1 is 0, A is 0, B is 1, output is 0. When 1, 0, 0, 1, 1, 0. When both are high, then and only we will get true, which means high. Otherwise, we will be getting 0, as we know about AND truth table. Now about the OR gate. The OR gate takes two inputs. Here we taking two inputs like A and B. If both are low, then output will be 0. If any one, at least any one is high, then we will get high. If, for example, as we can see 0, 1, we will get 1, 1, 0, we will get 1. And 1, 1 as well, we will also get 1. So in AND, it was like A into A dot B, and in OR is represented by plus sign between A plus B, between A and B. So like A plus B is OR gate. Also we can also set like AND is a AND operation, OR is OR operation. In AND both need to be high to get high input, and OR in OR any one need to be high, at least any one. Now the XOR gate. The XOR gate outputs 1 only when the inputs are different. Like here it is different scenario. If both are 0 or both are 1, we won't get any output, it will be 0. If any one is 0 or 1, we will get output. Like as we can see in 0 0 we will get 0, in 0 1 we will get 1, and 1 0 1, 1 1 0. The purpose of this, use of this is that it is widely used in adders and combinational circuit. Now arithmetic operation in binary. Binary addition follows simple rule. For example, 1 plus 1 gives a sum 0 and carry 1. Subtraction is done using 2's complement. This allows the same circuit to perform both operations. As we know about combinational subtraction and uh, subtraction and adding circuit, combination circuit. A full adder adds three input A, B, and a carry in. And now it produces a sum and a carry out. Multiple full adders are connected to a form of a multi-bit adder. As I told you, input A, B, and C in. It adds three input in a full adder. Also, I forgot to mention that in earlier slide, like I just mentioned that if 1 plus 1, the carry will be 0 and carry will be 1 and sum will be 0. In a full adder, if it is 1, 1, 1, then the carry will be 1 and the sum will be 1 as well. Okay, now a multiplexer selects one output from the multiple inputs is uses a select line to choose the desired operation result. In ALU, it chose between and sub results. Here we can see 2 to 1 marks. If 0, the output line is D0, 1, the output line is D1. Now, the operation table. The operation is controlled by select line. 0 represent and 0 represents the OR, 1 0 represent add, and 1 1 represents sub. This defines how the ALU behaves. As we can see as well in operation table, 0 0 is AND operation, logic is AND gate, 0 1 is OR operation, gate used is OR gate, 1 0 is add, the logic gate we use is full adders. Full adders contains many logic gates. 1 1 is a subtraction, which is full adder plus inverters. Now, 4-bit ALU design. The 4-bit ALU uses the 4 full adders connected in sequence. Each handles 1 bit. Carry flows from one stage to next stage. Carry flows from, as I mentioned, all operation has controlled using common select lines by multiplexer. Now, working example. For example, A is a 4-bit binary number 1010 and B is 0101. Let us trace through all four operations. Now, if OP code is 00, as we know, it will do AND operation and the result will be 0. Because as we know, 01 is 0 in AND operation, 10 is 0, 01 is 0, 10 is 0. Now, in OP code is equal to 01, the OR gate gives the OR operation and we will get result 15 because 10 is 1, 10 is 1, 01 is 1, and 10 is 1. So 1, 1, 1, we will get 15. Now add, now OP code 10, we will add both numbers. So 1010 plus 0101, we will get 1111 as well. So the output will be 50. Now the OP code 11, for that we will do subtraction. So 1010 minus 0101. So the output will be 0101, which is 5. If we multiply it with its weight value, like 2 raised to 0 into 1 plus 2 raised to 1 into 0 plus 2 raised to 2 into 1 plus 2 raised to 3 into 0. So it will be 4 plus 1 is equal to 5. So the operation depends on the OP value, which OP value we are selected and what we want in the output. Now the advantages of the ALU. The ALU is fast, simple, and reliable. It performs operations quickly. It is easy to design, and it produces consistent results. Now the limitations of the ALU. The ALU has some limitations as well. It supports limited operations. It also works on fixed bit width. More complex operations require additional hardware. That's the limitation of the ALU. And the fixed bit widths mean 8 bit, 16 bit, 32 bit, or 64 bits. Nowadays, we also use 86 bit or more. Where is ALU is actually applied in real life. ALUs are used in CPUs, embedded systems, and digital devices. They are essential for all type of the computing system, like central processing unit, as I said, CPU, in embedded system, and digital devices like smartphones, tablets, and IoT-based devices. And the now final conclusion. To conclude, the ALU is a fundamental part of computing. It is built using simple logical gates but performs powerful operations. Understanding ALU help us to understand how computers works internally. We can also say it is like a basic block of computer. So thank you for listening to me. And if you have any doubts, please let me know in commentation. I hope this presentation was informative.